Hi guys, let's continue messing around with OpenCascade library, and today I want to speak about one data exchange workflow. The idea of this lesson was inspired by my good old friend Mladen. Hi Mladen. The idea is that we design something simple, we prepare some simple object hierarchy containing, some simple cylindrical primitives to represent this car chassis, which we've been talking about in one of the previous lessons. And then we try to associate different colors and names to different components and export this whole thing to a step format, to a step file. And this is quite useful because this way you would be able to communicate not only geometry of your product using OpenCascade, but also some metadata. And later on in the receiving system, you could take advantage of this metadata and, define boundary conditions on specifically labeled boundary elements. You can define materials or subdomains. So this is something you might want to do if what you are developing is, for example, simulation software. So let's go ahead and try to make something like that. To start off, you can go to our repository with all the lessons and pick up this lesson number 15. So you can clone this project over here and then configure it with CMake, like we usually do. And we are going to start almost from scratch. So here I have almost empty main function. And what it does here, it simply initializes a viewer, as we usually do, when it creates a smart pointer to our XDE document when there is something related to visualization, and we are not going to speak about it because it was covered in lesson number 12. So the first thing we need to do, we need to initialize our document, and for that what we need to have an application. So let's go ahead and create this tdoc std then application, and this thing of course should be included in the first place. Alright, and then if you remember, we need to put a magic string here to specify the format of our document. So this is going to be bin OCAF drivers, then define format. And this way we define the format of all the documents which are going to be managed by this application. So we have to go and include this class also here. To create a new document, what you have to do, you need to call this new document method on your application and pass here the format string, which is bin OCAF. Bin stands for binary. So now we have this empty document and we can start populating it with data. And for that we have to agree on what we are going to have in our document. To represent a car chassis, what we can have one wheel which is going to be instanced 4 times in 4 places of our model, and we can do it like that, or we can also design sub-assemblies which would contain a couple of wheels connected by an axle rod. So let's go ahead and prepare a function which would build a wheel model or wheel geometry for us. It's going to return topo.ds shape, and it would accept like an outer diameter of our wheel and also its width. There we go. And here I'm going to use an API of OpenCascade to build a cylindrical primitive, which is brep prim API then make cylinder. When we are constructing this sort of cylindrical primitive or our wheel primitive, what we have to think about is how it's going to be oriented with respect to the entire chassis, of course. And whenever you design a part, you have to think of it in terms of its local coordinate system. And then, once you drop it into the assembly, you give it a different placement. So right now we do not have to think about its ultimate placement in the assembly, because this is something we are going to adjust later on. But we have to think about its local referential. And here I'm going to orient this wheel. I am going to give it its local axis. Here is the origin point, which is 0, 0, 0. Then I am going to give it an axial direction, which is going to be, in my case, the x. And okay, for the radius, we are going to use this outer diameter divided by 2, and for the height of the cylinder, we are going to use our width parameter. There we go, and actually I can just go and return this whole thing, because it overrides a conversion operator. So that this makeCylinder class can be converted to TopDS shape, which is our brep geometry for a cylindrical primitive. What I want to have another function which would create an axle. Alright, here I can also use it like a cylindrical primitive, because axle is a cylindrical rod, and I'm going to give it like 2 parameters. One is diameter of the axle, and then length of the axle. And why not just go and reuse the same thing from here. Alright, so let's go ahead and try to add those 2 parts into our assembly. And if you remember from our previous discussion of XDE and assemblies in OpenCascade, there is such a term as a prototype, and I'm going to make it explicit here, so I'm going to create a structure like tprototype. And let it store our TopDS shape, which is going to be the shape of our part, or it can also be a shape of our assembly, and we will see later on why it's necessary to have a shape for an assembly in XDE. And another thing is TDF label, which is going to be a persistent representation or persistent ID of our prototype of our shape in the XDE OCAF document. There we go. We do not need to have a default constructor in this tprototype structure, because this TopDS shape thingy here is a sort of a pointer, and it will be initialized with a null shape, and this TDF label is the same sort of thing. It contains a pointer in itself. If you go inside it, you will see that there is this pointer somewhere below. I think, yeah, this is TDF label node PTR, which is a pointer, and in its constructor it will be initialized with a null pointer, so we do not care about this uninitialized memory issue here. Alright, so now we can create a prototype for our wheel, and for that let me declare an instance of this tprototype structure. Let me call it like wheel proto, and let's initialize it. So I'm going to initialize its shape using my function, which is this build wheel. And the second stage would be to initialize its label, and the label could be initialized if I add this shape to my XD document. So to run this build wheel function, I need to have a couple of parameters. So let's declare some outer diameter. Why not to have it like 500 millimeters, and then the width could be, I don't know, 100 millimeters. So we can pass these 2 arguments here, and notice that this sort of invocation is a little bit like parametric modeling, because you see that I'm running this function with some parameters, and if I change those parameters, this primitive will be reconstructed. And this is one way how would you build up a parametric modeling system using OpenCascade. So we have this build wheel invocation, which is supposed to initialize our shape property of a wheel prototype structure, and now I need to add this shape to our XD document. And for that I am going to use what's called a tool, or XD tool. If you want to manipulate with an XD document, you need to get used to this tool concept. And there are 2 tools which we are going to use today. One is a shape tool, which is supposed to give you all the API to manipulate with assemblies and parts and prototypes. And another is a color tool, which we are going to use to work with the colors of our prototypes in the XD document. So let's go ahead and prepare an instance of our shape tool, which is going to be XCAF doc then shape tool. This thing I have to include. And to initialize it, I'm going to use what is called XCAF doc then document tool, and its static function, which is a shape tool. And here I have to pass a TDF label, and it's completely fine to pass here just the main label of my OCAF document. Like that. This is for shape tool, and the same sort of invocation I'm going to use to access a color tool. So let me just go ahead and include this document tool so that I can use it, and also include this color tool. There we go. And now, using this shape tool, I can add my shape to my document. To do that, let's use a method which is add shape. Here I pass my wheel proto, then shape. And then there is this boolean flag make assembly. And since I'm not going to add an assembly and I want my shape to be like a part, I'm just going to pass like a false here. And there we go. Alright, so now I would suppose that my document is sort of initialized and that I can use these visualization facilities to see something on the screen. Let's go ahead and run this application, and you see I have my sort of wheel prototype here on the scene. Now I want to add an axle as well, and for that let me declare another prototype, which is going to be like axle prototype. And here I also have these two fields, one is shape, another is a label, and here I'm going to run this build axle. For the diameter I need to have like another property somewhere, which is going to be just, I don't know, d, which is going to be the diameter of my axle, so it has to be smaller than this value. And then I also have a length of my axle, and let it be, I don't know, maybe 500 or something like that. And then I have D and L here. And in the same manner, once I have this shape, I can add it to my document as yet another prototype. So that I will have these two prototypes, wheel prototype and axle prototype, that actually do not know each other. They are completely isolated from each other. And the next stage would be to drop them into a single assembly. So let's run it like that. And I'm going to see what's going to change. Yeah, you see that there is my axle and the wheel, and they sort of badly interfere each other, and I want it to be, I want to change a bit how these local coordinate systems are defined, and for that let me change something in this code here. Instead of using the origin point, I want to use an explicitly defined point where I'm going to use this width parameter to move a bit my wheel so that it's going to be symmetric with respect to y or z plane. Here I have this coordinate and then two zeros. And for the rest of the code it's going to remain the same, and the same thing I'm going to have here. I want to have a center point of my axle in the origin point of its local coordinate system. So for that I'm going to use something like -L divided by 2. And the rest of the coordinates are going to be 0. So let's check what's going to happen if I draw it like this. And you see that this is a more symmetric scene. Why I have done this sort of modification is to simplify a little bit how would I define transformations later on when I need to instantiate this wheel twice to move it here to the right and to the left, so that to compose my wheel axle subassembly. Of course, I could keep using the original definition of these primitives in their coordinate systems, but it's not going to be that convenient for me. Alright, so let's close it for now. And now I want to add the first prototype of my assembly. And assembly or subassembly is still a prototype, because a prototype is something which is going to be instantiated later on, as we discussed in one of the previous lessons. So let's declare a prototype, which is going to be wheel axle proto. And as usual, I need to initialize shape and a label of my subassembly. And actually here there is one tricky point which is not easy to explain. Why actually would you need to have a shape for a subassembly? Because if you think about it for a moment, you will shortly realize that a subassembly is simply a hierarchy of already defined shapes. So why would you create another shape? And here, I mean, I do not have any good explanation for you. It's a design decision of XDE. In XDE, it's necessary to have shapes for everything. It's necessary to have shapes for, for parts, for subassemblies, for assemblies. And the shape for a subassembly is going to reflect the hierarchy of labels which you are going to end up with in the XDE document. So let me show you how it works. Here I'm going to declare another function which is going to build my wheel and axle shape. And I'm going to return the OpenCascade shape, which is sort of a compound shape. And here it's going to accept the OpenCascade shape of my wheel, then my axle. I'm also going to pass here the length of my axle, because okay, it's sort of encoded here in the axle definition, but I want to have it explicitly in order to compute the transformation, which I need to take in order to put my wheels with respect to the midpoint of an axle. So here I pass also this length of my axle. There we go. So in order to make things work, what I'm going to do is I'm going to add prototype shape of my wheel axle assembly to the XDE document using the same shape tool. That's why I need to compose a shape representing my subassembly. And this shape is going to be a compound, so I declare this OpenCascade compound. And to allocate a compound in memory, I need to use a tool which is a brep builder, and its method which is make compound. So it's basically not enough just to declare a compound like this, because it's going to be a null shape. And the first thing I have to do, I have to allocate heap memory for this compound shape, and to do that I use this brep builder, and then it's make compound method here. Once I have it, I need to add a couple of shapes into my compound, and for that I'm going to use this brep builder, then add, and here I'm supposed to insert this component shape, which is C, in the signature of this add method, to my compound shape, which is S here. So basically I need to do something like that. I need to add this wheel to my compound and also this axle here. The problem with this code here is that if I keep it like this, when I'm going to end up with a compound containing just one wheel, which is positioned in the center of my axle, which is clearly not what I am going to have. So I need to compute a couple of transformations actually. So let me declare transformation matrix, which is a GPTRSF, and one transformation is going to be my wheel T right, which is a transformation to move my wheel prototype to the right of the axle. And I can declare this transformation as a pure translation, so that I can go like set translation part, and here I define a vector of translation, which is going to be gpvec, and then I am going to move my wheel along the x-axis to the L divided by 2. And the same sort of thing, the same sort of transformation I'm going to take for my left wheel. And the only difference here is that I'm going to take it in the negative direction with respect to the x-axis. And now, instead of adding this wheel directly to my compound, I'm going to add an instance of it, or a transformed copy of this shape, which is going to reuse just the same boundary description from the shared memory, but with different transformation matrix associated. So I'm going to use a method which is moved, and here I pass this wheel T, then right, and for the left wheel I'm going to use this wheel T left. And finally I can just go and return my compound shape, which would represent my assembly. So now I can take advantage of this method, and here I have to pass a shape of my wheel, which is a wheel prototype shape, then axle prototype shape, and finally this L, which is the length of my axle rod. Of course, here I made a mistake. And now I'm ready to add this shape to my XDE document using shape tool. Add shape, Then I pass this shape as the first argument, and instead of passing false as a second argument, I'm going to pass true, because I'm going to create an assembly right now. So there we go. And let's see what's going to happen visually. You see that I have this sort of wheel axle, and you can see also that there is no this cylindrical primitive anymore in the middle of my axle, and instead of this I have these two primitives, these two instances of my wheel on the left and on the right of my axle. And this is what I wanted to have actually. You may wonder how it's all organized in the data structure of the document, and to check that, let's make a diagnostic dump of our document. So what I want to do now is I want to dump my document to file system and then open it back using OpenCascade inspection tool and see what actually we have inside the document in terms of labels and attributes. So for that, what I can do, I can go like up, which is my OCAF application, then save as, and here I pass my document instance, and then, yeah, there is a signature that accepts a file name or path name. So here I'll just use a hard-coded something. And the format of my document is going to be XBF because it's a XDE binary format. I can also check what is the storage status, if it's okay or not. So for that I can go like pcdm, then store status as status. And the status should be okay. So I have to check that if store status is not pcdm store status okay, then I have to return an error. Alright, so let's try to run it like that. And now you see that there is this XBF document which I want to inspect using native OpenCascade tools. So to open this document I'm going to use OpenCascade Draw. This is a draw console, and here what I can do, I can load all the plugins and then use this command which is open. It starts from uppercase O, and then the first argument is going to be the file name, which is in my case docxbf, and then I have to give it like a document name. So you see, there we go, and I can check what is doc, it's a tdoc std document, and I can go like DFBrowse, then doc. So here's my document. You can see that what do I have in this document is a couple of solids. You see that I have two attributes, a name shape containing this topodst solid, then I have an assembly and three components in my assembly. And you can trace those links here, and you can see that these two components, they address the first solid, and the third component addresses the second solid here, which is, I suppose, my axle. And there we go. You can see that there is no kind of duplications. If I have two wheels in my assembly, I still have only one solid in my assembly, which is a good news because it means that I have instancing working. Alright, let's go on with our exercise and finally compose an assembly containing two-wheel axle prototypes, two-wheel axle subassemblies. For that I'm going to use the same principle, so I need to declare another function which is going to return a compound of two-wheel axles, and here it's going to be like build, I don't know, chassis. So I need to pass here a shape of my wheel axle, and the second argument will be the chassis length. Again, we start with creating a compound shape, and now I'm going to declare a couple of transformation matrices, which is a front transformation and a rear transformation. So what I'm going to do for the front transformation, I'm going to take this wheel axle subassembly and move it along the y-axis by CL divided by 2. This is the first transformation, and the second is going to be the opposite. And finally, I can just go and add my subassemblies, my located shapes to my compound as before. So I take this voxel shape and create a moved instance, a moved copy of this. It's a sort of a shallow copy. It's not going to duplicate boundary representation itself. And I only move it in space. And finally, I return my compound. There we go. So I can now go and declare another prototype, which is my chassis. Here I pass my voxel shape and also my chassis length, so that I have to declare it somewhere. Let it be just, equal to maybe length. And using the same logic with the shape tool, I'm going to add this assembly to my document. Add shape, then it's going to be the shape from my chassis prototype, and it's going to be an assembly. Alright, so let's see what's going to happen visually with our document. Okay, so this is it. I have this chassis. It's sort of what I wanted to have, although you can see that there is clearly some design issue, so maybe I have to reduce this, outer diameter of my wheel. Yeah, now it's a little bit better. And now what we can do, we can try also to dump this whole thing to a step format, because so far we have only this XBF file. And of course, this is a native OpenCascade format, which you cannot easily use in some third-party software. You cannot open it in CATIA or, I don't know, Fusion 360 or even in FreeCAD. So we need to get into some neutral waters in order to be able to communicate our design to the external world. So let's do this, and let's add a function which would write a step file out of our document. So it's going to accept this tdoc std document with our assembly, and also the file name. So to write a step file, we are going to use a tool which is step-caf control writer. I'll have to include it first. And then there are two methods which we have to run one after another. The first method is transfer. The idea behind this transfer method is to map all the OCAF entities from this document to the corresponding step entities, so that we will have in-memory data structure representing our step file. For that I'm going to pass here this document, and also you see that there is a mode which is sort of default mode, step control as is, and I can sort of use it. So I do not need to put anything else here, but if this transfer stage fails for whatever reason, I have to return false. This is one thing, and the second thing is to serialize the transferred model to a file. For that I can use something like a writer, then write. Here I need to pass this file name which I have as an argument. And if for some reason the status of this writer is not done, then I have to return false. Otherwise, I'm going to return true. There we go. So now I can write a step file as well, and I'm going to pass my step file as a parameter of my executable. So here, if I go in debug, debugging, then I have these command arguments, and here I can pass like a file name. So let it be just test stp. Alright, and if this file name is passed, it means that I have a second argument in my main function. So I can check this using this argc argument here. So if argc is greater than 1, it means that I have this file name passed. And then I can like write step, and then pass here the document and the file name which is going to be stored in argv1. So if this right step function returns false when I exit with error code here. Alright, so we can try to run it like this. And it seems that something happened. You see that there is this diagnostic message in the console coming from OpenCascade. So now I can try to open my step file. And there we go, we have this step file here. If I open this model in Fusion 360, I can also see this modeling result. I can also see this assembly structure here, and you can see that, okay, this is a solid, which is sort of instanced 4 times. And if I go and, for example, modify it, the modification will occur with all the 4 instances of this solid here. It means that instancing is working. The only problem here is maybe that the names of these components of my assembly are not good because they do not reflect anything. I have an artificial assembly name here for my wheel axle components, and for solids I have just like this solid 1 and solid 2, which is not good maybe. Alright, so let's see how can we change names of our prototypes. And for that there is no interface which we are going to use actually in XDE, and instead we are going to use some low-level OCAF manipulation. Fortunately, we have all the labels already stored in the corresponding data structure, so it's not going to be a big deal. For that, we are going to use tData std name attribute, which is a sort of Unicode string in OCAF, and we are going just to settle down this attribute to the corresponding labels. For example, if I had this wheel prototype, I can take its label here and settle down this tData std name attribute to this label and pass as a second argument the name which I want to have. Let it be just wheel. In the same way I can associate names with other prototypes, like axle prototype will get this axle name, wheel axle prototype is going to get this wheel axle name, and finally chassis prototype will get chassis name. There we go. So the only thing which is missing right now is this attribute has to be included. Alright. So we can associate names with our prototypes as simple as that. Let's see what's going to happen if I run this application once again. The step file is going to be written right along with the execution. So now I can go and check my shape in Fusion 360. So I'm opening my test file, and you can see that these components here, they got the names which I wanted to give them. I can also do the same thing if I sort of open this assembly as an XDE document in Analysis Situs. What I have to do, I have to open my step file as an XDE document. For that I go like awesome XDE, then load. I give my model a name, which is m, and then the file name, which is going to be the file from my desktop. Alright, so now I have this model, and I can browse its contents like awesome XDE, then browse. And the model is M. So you can see here the structure of the XDE document. This is actually a scene tree, and you can see that, okay, I have this root assembly, which is chassis, and it gets its name, which I assigned as a tData std name attribute. Then I have a couple of components. They do not have any meaningful names because I didn't assign any names to the components. But if we go down by the hierarchy, we see that there is a wheel axle prototype, which is a subassembly, and then there is a wheel prototype. And you can also see that instancing is working because this persistent ID here is reused as many times as many wheel occurrences I have in my document. And the same applies to the axle. You see it's 114 in this subassembly, and since this is exactly the same subassembly here, we have this axle reused also here. So what we can try to do, we can also try to give some meaningful names to these components, to these instances here. For that, what we can do, we can run a child iterator, which is a TDF, then child iterator, and iterate all the direct children of our root prototype, of our root assembly. This is this chassis proto label. So then we go like CIT, then more, and CIT, then next. That's a kind of a usual way of iteration in OpenCascade. And I need to include this iterator right here. Alright, so now if I take a value of this iterator, then it's going to give me TDF label. And since I'm iterating the direct children of my assembly, these are the components, so that I can name it like component label. And now using the same mechanics, I can associate like a name with this component label and name it like, I don't know, wheel axle ref or wheel axle instance. There we go. So now we can run this application once again. I only have to close the previous instance of it. And now let's see what I am going to have if I read this step file once again. You see that now these instances are named. And if you know the order of them, then you can also give them some meaningful names if you will. What remains to be done is some coloring maybe, because right now we do not have any colors associated with our assembly. And for that I'm going to come back to this color tool. If you remember, we have it here. And using this color tool we can associate colors with our parts, instances, assemblies, and it can be done very easily. So we are going to use this CT, which is a color tool, and then set color. And here I need to pass a label. If I want to colorize a wheel, for example, I take its label here. Then I define a color which I want to use. Here it's a quantity color, OpenCascade's data structure, and let it be just a red color. So in RGB it's 100, and I only have to precise a notation, like it's a quantity, then RGB. And one last thing which I have to specify, you can see it here, it's XCAF dog color type, because in XDE there are colors of different types. If it's a part level color, then it's going to be this XCAF dog, then color gen, this one. So there we go. Like this I can associate a red color with my wheel prototype. And in the same manner I can colorize an axle, and let it be like, I don't know, green. And here I also use this part level color. And you can see that, okay, if I just visualize it here, I already have my parts colorized. And to check that it still works in third-party software, let me open it in Fusion 360 as well. And there we go. One thing which I also wanted to draw your attention to is, we want to be sure that instancing works, and so far in the viewers which we used, like the viewer from Analysis Situs and also the viewer inspection tool of OpenCascade, we can see that, okay, this instancing is kind of working well, but I also want to show you how you can check it without any viewers. For that, you can just go and find your step file and look inside it. And here, if you just open your step file with any text editor, actually you can search for manifold solid brep. Like this is an entity in a step format which corresponds to our solid object. And if you search for it, you will find that, okay, there is one solid brep here and the second is here. And we have only two manifold solid breps. It means essentially that in this step file you have just two solids defined, although in the assembly we have 6 objects. And that also means that our instancing works. One maybe last thing for today is, okay, we colorized and we associated with metadata, which was a color in our case, to our parts. But what about subshapes? What if I want to colorize a single face, for example, in my part? How can I do that? And actually it's still possible. You can do it with XDE framework. For that, we just need to know exactly what is a face we are going to use as an attachment point. So for example, here, if I come back to Analysis Situs, if I browse my document once again and visualize this subassembly, okay, I do not have any colors right here, but if I want, for example, I can also visualize this wheel. You see it's defined in its local referential, and let's say I want to colorize this top face here, and its index is 2, and this is the information which I can use when I work with metadata at OCAF level. So if I want to colorize this face, I first need to index all my faces. So for that, I use a package which is a top exp, then map shapes, and here I pass my shape of the wheel prototype, and I'm going to index all the faces and put these faces into a collection which is top tools, indexed, then map of shape, all wheel faces. And before I continue with that, I would also like to improve a bit my interface here, or my auxiliary data structure, because I want to derive like wheel prototype from my prototype, which is going to become like a base data structure. And here in the wheel prototype, I want to declare something which I would call a front face, and it's going to be topods face, front face, the face which I'm going to colorize. And this face in XDE, in OCAF, it's going to get its own label. That's why I also add here front face label. And now when I create this wheel prototype for the first time, I'm going to use this T-wheel prototype instead of this T-prototype base structure. And now once I know the face which I want to colorize, I can initialize these two remaining fields of my data structure. So the front face is going to be the second face in my indexed map. So I'm going to take the second face here, and I only have to cast it to the face type, because if I just keep it like that, it's going to give me topods shape, and I need to convert it to topods face in order to be able to initialize this field over here. So let's include this thingy here, which is topods. Alright, and once I have my subshape initialized in the data structure, I can go ahead and add it to the XDE document using exactly the same shape tool which we have been using all day long. So we can go and call something like add subshape. This time it's not add shape, it's add subshape. Alright. Here we need to pass the label of the parent entity. For us it's this wheel prototype label, which is a part label for our wheel, and then we need to give it our front face, and XDE will automatically find that this front face here is a subshape of this wheel prototype shape, and it will add the corresponding label to the XDE document. And once we have it done, we can associate a color with our front face label, because we now have it explicitly in our XDE data structure. So let's go ahead and use this color tool and attach like a color, let it be just like a blue color here, to our front face label. And this time I'm going to change this general color or generic color to surface color. You can go inside this color definition enum, and you will see that there are 3 types of colors. Like one is to be applied to the part, and if you want to colorize faces, you have to use this surface color, and if you want to colorize edges, then you have to use this curve color here. There we go. So let's see what's going to change if we do it like this. And you see that the front faces of my wheels are now colorized. And the only problem here is that maybe I should have mirrored these wheels when I moved them along this axle road. But instead of applying mirror transformation, which is always not a good idea in OpenCascade, I would like just to flip them by rotating the corresponding prototypes around their local y-axis. So let's go ahead and fix this last remaining thing, and I'm going to come back to this build wheel axle function and change something here. That's actually not a big deal, and I'm pretty sure that you can figure it out by yourself, but I want to show you what's called a quaternion in OpenCascade, because this is how we are going to specify the rotation transformation. And for that, what I'm going to do, I'm going to declare quaternion data structure here. I think I have to include it as well. And using this quaternion, I'm going to specify rotation, which is going to be the rotation around my local y-axis by pi angle. So I'm going to flip my orientation like that. This is a quaternion data structure, and now I want to turn it to GPTRSF. Like let it be just R, which stands for rotation, and I will initialize it like set rotation, and you can find out that this set rotation accepts our quaternion type here. So now I have this rotation data structure, and now I want to compose this wheel T left transformation as a composition of two transformations. So first, what I'm going to do, I'm going to flip my wheel around its local y-axis, and this is going to be this R, and then I have to multiply it or pre-multiply it by my inverted right transformation. The order of transformation matrices in this equation here is of great importance, so you need to be sure that this R transformation is applied first, and to be sure about that, you have to put it to the right of this equation. So I'm going to use this inverted copy of my right wheel transformation and then multiply it by R. And finally, I can just get rid of this set translation part, and this left transformation will be applied as it was applied before. So let's see what's going to happen if I do it like that. Alright, and you can see that everything is working perfectly well. And this coloring is going to be also compatible with third-party software, so I can go to Fusion once again and open this step file in Fusion. So you can see that it's nicely compatible, and I have this colored subshape also in Fusion because this information is actually transferred to a step file. So that's it for today. I hope you understand better now how could you employ this XDE framework into your own workflow, what you can benefit from this framework, and its major advantage, the major advantage of having this XDE as a medium to represent your engineering data is that you do not have to implement these assembly data structures with all the metadata by yourself. And this is pretty easy to get this XDE framework populated from a step file, and also if you have this XDE framework filled with the data, you can easily write it or serialize it to a step format without spending much time how to map your specific data structures to one or another step entity. So everything is already implemented for you, and you can just take what exists. So thank you for being here. If you have any questions, feel free to post a comment down below, and see you in the future series.